Hey there, everybody. Welcome to a video over sections 7.6 and 7.8. Each of these sections is fairly short, at least what I'm going to cover from them. So hopefully this video is brief. I'm just going to hit the highlights of both sections. How do you deal with eigenvalues that are either complex or repeated? So we're going to continue our parallels with chapter 3 when we ran across complex or repeated solutions to that characteristic equation. So the point of this section is just to ask, if you got a matrix system like we've been dealing with and the computer spits out complex or repeated eigenvalues, what do you do with that? So here's an opening example. If we had a system like this and we tried to solve it like we did before, I've written it in non-matrix notation here just to be completely clear about what the system is. So if you want to try to solve this like we did last time, then you ask a computer for the eigenvalues of the matrix negative half, 1, negative 1, negative half. And what the computer will spit out to you are these two values here, negative 1 half plus I and minus I. And it will give you these two choices of eigenvector. And if you were just blindly doing what we did last time, you would say, all right, C1 eigenvector e to the corresponding eigenvalue t plus C2, the next eigenvector e corresponding eigenvalue t. That's what you would do. Just like in chapter 3, though, if you're going to write solutions like that, it raises an immediate question. What does any of this mean? So if this is trying to model, say, two populations over time or something, this is kind of meaningless information. So just like back in chapter 3, you have to take the complex stuff you've gotten and distill from them some kind of real solutions. Like, I want to be able to graph x1 and x2 in the plane to see what they're doing over time. I can't graph things like this because I got an e to the I. What does that even mean? So the general approach to doing that is as follows, and it's very similar to chapter 3. The first thing to point out is that actually from a purely mathematical standpoint, this is fine. Like, that doesn't bother me any when you write that down. I like that. But, again, just like in chapter 3, complex things there were also fine, but if you want to live in the physical world, then you have to take what we just got and get from them something real. And the technique we're going to use is an application of this theorem here, the theorem from your book, 7.4.5. It says this: suppose you have a solution going that looks like real stuff plus I real stuff. So you have separated out the two pieces of the complex solution. You've written it so that there's just a single I. You have stuff with no I attached. You have stuff with an I attached. You've written it like that. Then it turns out that if you pull off just the U stuff and the V stuff, you pull apart the two real parts, each of those are actually also solutions to the original system. And so what this theorem lets us do is build sort of a general complex solution and then just pull apart that solution to get real solutions from it. If this seems abstract or whatever, it's totally fine. I'll show you an example, but that's the general approach. We'll get sort of a complex solution going, break it into two pieces, grab those two pieces, and those will be the basis of our real solutions. So let's go back to the example we started with that had complex eigenvalues negative half plus or minus I with these two corresponding eigenvectors. Our goal is to eventually write something with a C1 and a C2 in it. C1 stuff plus C2 stuff. It was a 2x2 system, so we need a C1 and a C2. So since a single complex solution will give rise to two real solutions per that theorem I just showed you, you can use the following technique to get yourself two real solutions and slap C1 and C2 on them. So let's just pick one of the complex deals we had going. So notice this is a single complex solution. So I've got my eigenvalue negative half plus I, and my corresponding eigenvector here, that corresponded to negative half plus I. Now I should point out that if we did this in class, I would ask Wolfram Alpha at this point, what are the eigenvalues, what are the eigenvectors? Wolfram Alpha is not always completely consistent with how it outputs the eigenvectors here. So depending on what you're looking at, if you're doing this yourself, it might give you a different eigenvector here. It might give you I negative 1 or something like that. So the thing is, each eigenvalue has infinitely many eigenvectors. So Wolfram just gives you a nice clean one, but it doesn't always choose the same one. So just to acknowledge that if you're doing this on your own following along, your exact vector here might not be the same as mine. That is totally fine. It of course will affect what you write down, but it won't change the final answer in the end. Everything will be the same. So back to this, I have a single eigenvector, e to eigenvalue t, and notice I don't even have my c1 here. I'm just dealing with a single complex solution, a single one. Now I could have, if I wanted to, done negative half minus I up here and put the other eigenvector here for negative half minus I. It doesn't matter when you have this information. It doesn't matter which eigenvalue you grab when you do this analysis. You just want to be consistent. So if you're going to mess with negative half minus I, you do have to grab its corresponding eigenvector. So I decided to mess with negative half plus I and then mess with this eigenvector that Wolfram gave me. So you grab an eigenvalue, slot it here, put its corresponding eigenvector there, and then we're going to just mess with this until we can get separate I stuff and non-I stuff. So first, note that when I write this, I can just distribute the exponential into the vector if I want to. So that's all I've done here. Put it up top, put it down below. I got my I right there. Multiply by 1, multiply by I. So now I just want to take this and break it into pieces that look like this. Real stuff plus I real stuff. That's my goal. So I'm going to show you how to do that. Well, the first issue is that you have this I up here in the exponent. That's a tough one right there. It's not even clear what that means, e to the I. So the first thing you want to do is not have i's in the exponent. And so recall from chapter 3, we actually saw this in chapter 3. We didn't do anything with it, but we did see it, that e to the a plus bit, it turns out, is e to the at times quantity cosine of bt plus I of sine pt. This is something you just have to know. It comes up in every one of these complex eigenvalue problems. So e to the quantity a plus bi t, it turns out, is e to the at times all of this stuff. And this is true simply because this formula we also saw back in chapter 3. So you can know this one or not, I don't care. It's a special case of this top one. This top one comes up all the time. How do you deal with e to the a plus bit? Like this. Notice now there's no I in the exponent. There is an I still there. You haven't gotten rid of the I, but the only exponent now is this at, and you have gotten rid of the I up there. No I there. Okay, so here's the first observation, that if you're dealing with something like this, e to the stuff t, well, that stuff involves an I. If you want to, and you have to in these problems, you cannot have the I in the exponent anymore using this formula. So let me just show you that formula. Okay, so here, what have I done? I've just used that formula with, let's see, a is negative half, and b, notice, is 1. Coefficient on I is 1. So down here, e to the a plus bit, a is negative half, so there's negative half times t, and here's cosine of 1t plus I sine t. So I just took this thing here and applied this formula to it. So make sure you understand that. And then once I have this equality going, I can just distribute the exponential in if I want to. That's all I did there. I distributed the vector and the exponential, so I apply it to a cosine, and I apply it to the I sign. That's all I did. So this first equals is that formula involving complex exponents. The second equals is just distributing. And then I put everything inside. So I put this up there with the 1. I also put this down there with the I. I put this up there with the 1. I put this down there with the I. And I combine everything. So 1 times this plus 1 times this becomes a single entry in one vector. I times this exponential stuff cosine plus I times this exponential stuff sine becomes a single entry in the bottom of a vector. And then finally, I can take all of that and separate I stuff and not I stuff. So this e to the negative t over 2 cos t, no I. This negative down here, negative e to the negative t over 2 sine t, no I there either. So I just separate everything apart. So I have two I terms, two non-I terms. I separate them, and then the I itself, I just shift it outside. So I can like factor it out of that vector. So these 4 steps, these 4 equals, this is how you do any of these problems. And now we are basically done. So let me just summarize what we did here. We grabbed a single eigenvalue and a single eigenvector, and we formed this product like we're used to doing, eigenvector times e eigenvalue t. We then processed what e to eigenvalue t meant in terms of the complex exponent. We basically moved the I down from the exponent. Then we distributed. Then we grouped everything into a same vector. Then we pulled the I out, separated and pulled the I out. So that now we have real stuff, notice there's no I here, plus I times other real stuff. These steps will always be the same. What will change are the numbers. Like that might be a 5 minus 7I. This might be a 2, 6I, whatever. But the numbers the process is always the same. Whoop. Okay, so by that previous theorem, each of these individual pieces here, like this piece and the stuff attached to the I here, those are both individual solutions to the original system of differential equations. So now we're allowed to just slap a C1 on the first piece and a C2 on the second piece, and we're done. And if you don't like the matrix notation, as always, you can separate it and say, well, x1 is this, x2 is this. x1 you're reading across the top, x2 reading across the bottom. That's it. Okay, so that's what section 7.6 says to do. That's all I want from section 7.6. There's some other stuff in there, and also the book does prove some stuff to you, but every problem in 7.6 can be done like this if you want the general solution. Okay, so that's section 7.6. What if now you have a system where the eigenvalues are repeated? And by the way, you'll know it's repeated when you go to type this in. So eigenvalues, let's see. 1, -4, 4. This is a 2 by 2 matrix. It only gives me one eigenvalue, one eigenvector. I'm expecting 2 of them. It only gives me 1. That's how you know you got something repeated. Here we go. No. There we go. Okay. Up. Okay. Make sure I didn't. Not sure what's going on. Here we go. Okay. So since you have something repeated, -3, and then that's the corresponding eigenvector, you might be tempted just to kind of blindly go along and say, okay, well, C1 eigenvector, e to the eigenvector t, plus C2 eigenvector, e to the eigenvalue t. But if you do that, just like back in chapter 3, like you've just copied and pasted the same thing, replaced the C1 with a C2, you haven't done anything with the second part. This is all totally redundant. You need 2 separate deals, like 2 separate kind of like fundamentally different solutions from which you grow all the rest of them. So you can't just write this down. There's something missing. Okay, so what do? There's just a general theorem. It says, all right, and it only applies to 2 by 2 systems, by the way. So back in chapter 3 and chapter 4, when we had repeated roots of the characteristic equation, we could just deal with 8th order equations, things like that. That's no longer the case, actually. So when you have a 5 by 5 system or something, you can't just translate this theorem. But it says this: if you have a single repeated eigenvalue, here's just a formula for the general solution in the 2 by 2 case, where here gamma is the corresponding eigenvalue, and eta is what's called a generalized eigenvector. And when you open Wolfram, it will give this to you. See, it says one eigenvalue, -3, one eigenvector, and then it says, hey, for -3, there's also a corresponding generalized eigenvector. It's that. So you basically just grab both these vectors and slot them into the solution here. The regular eigenvector goes there, The generalized one goes there. Notice you pick up a t, so that's pretty similar to chapter 3. But you don't just pick up a t. You pick up this other thing too. So that makes it different from chapter 3. Okay. So just for example, back to this example we were doing, forget about the initial condition for now. You come back and do that later. That theorem just says, all right, once the computer shows me -3 is the eigenvalue and the only one, eigenvector 1, 1, and generalized eigenvector 1, 4, 0, I just crank this formula out. This is just that formula from the previous slide, making sure I put a t right there. And again, just emphasizing, if you're following chapter 3, you might just put a t right there and not do anything else, not include this. But for reasons that aren't clear to you, because I haven't proven anything to you, you actually do need this extra term now when you're dealing with systems, instead of dealing with just that single differential equation in chapter 3. So that's how you deal with repeated eigenvalues, just this theorem. So let me point out to you, we now know what to do in the 2 by 2 case, at least, whether we get 2 real distinct eigenvalues, complex eigenvalues, or repeated eigenvalues. Because this theorem only applies to 2 by 2 stuff, we actually don't know what to do if we had like a 4 by 4 system and we got a bunch of repeated eigenvalues spit out to us. So unlike with chapter 3, we haven't like completely characterized everything. There's still some mystery here. Things get really complicated with matrices when you start having repeated eigenvalues. So we're actually in this course not going to completely characterize everything. We're going to leave that sort of on the table, unlike in chapter 3 where we could do everything. All right, so coming back to this example, if you're given an initial condition, you of course have to process it. So you have to plug in 0 for t. So if I do that, all the exponentials become 1. If I plug in a 0 for t, notice this term just dies out. So in the end, I get like this equation here. Plug in a 0 for t, then the x vector becomes 3, 2. And now you solve this just like you do any sort of algebra 2 problem. So this is saying that 3 is c1 times 1 plus a quarter c2. It's if you read across the top. If you read across the bottom, it's saying 2 is 1 times c1. So you pretty quickly learn that c1 is 2. And then from that, you can deduce what c2 is. It's 4. And so here's the specific solution to that equation. So because it gave us an initial condition that allows you to nail down the c1 and c2 values, and there's your solution with a 2 and a 4. So those are sections 7.6 and 7.8. So your takeaway should be, if I'm given, a problem like this, initial condition or not, if a repeated eigenvalue comes out, I know what to do. If complex eigenvalues come out, I know what to do. To deal with a complex eigenvalue, a complex eigenvalue still come in pairs, so a single one of them will let you grow 2 solutions from it using this exact process. Write your vector here, write your eigenvalue here, and follow this process to get 2 separate pieces. That's how you deal with complex eigenvalues. Okay, so if any of this is confusing, make sure you shoot me an email. I'll still be in email contact while I'm gone. You can also ask when I get back if you would like. But that's sections 7.6 and 7.8.